So tonight will be an update on using the pan-tilt zoom surveillance camera as an astronomy camera. I got some time to do some more work on it. Let me just say the pudding is not done yet. So I don't have any lovely pictures to show you, but I can explain some of the things that I had to pay attention to. And let's just say I have a couple of, maybe a couple of thousand lines of C++ software that I've cut and paste from other things to do this. And it's coming along. I can actually see, the modules and shape and stuff, but it's not commanding the camera through the astronomy software driver yet, but I think it'll get there before the end of the year. So that will be tonight's presentation. But first, the news. So I don't know if you were paying attention, but the launch date for the James Webb Space Telescope, JWST or Webb, has moved out to December 22nd from December 18th. It will go off at presumably 7:20 a.m. Eastern time on Wednesday, December 22nd. The problem they had was nothing to do with the telescope itself. When the telescope is folded up, it's mounted into a collar, and the collar is then attached to the top of the upper stage of the rocket. So the collar is not a part of the rocket itself, and it's not a part of the telescope. It's between the two to hold the two pieces together. Funny thing happened. They put the telescope into the collar, and then they mounted the collar on the top of the upper stage. And shortly thereafter, the collar popped open. Now, once you're in the vacuum of space and you want to release the telescope from the upper stage, it's spring loaded, and there's a little mechanism that the electronics in the rocket triggers that says, let it go. And the spring collar opens up and a spring pushes the telescope away. Well, obviously in Earth's gravity, the vertical spring was not enough to push the telescope off the top of the rocket, but the collar sprung open with nobody doing anything. And they went, that's a problem, because as the rocket gets launched, it goes through a lot of vibration and pressure changes, and they didn't want it to accidentally spring open unexpectedly while it was still inside the fairing of the launch vehicle. So they said, give us a few days to figure this out, why it happened, how to make it not happen, or if it was just a one-time anomaly, at least, why it happened. And it took them a few days to do that. And the very first thing they did was say, stop, give us time to figure it out, move the date out. We may be able to launch it sooner, but just set a new launch date out a few days. So they moved it from the 18th to the 22nd.
I thought that they were testing to see if there was any damage caused by the vibration.
No, that's what they had to test of the telescope itself. But this collar is something that is not supposed to open all by itself.
Yeah.
It's supposed to only open in the vacuum of space when there's no gravity, and the spring pushes the two apart, which gives the telescope a little bit of oomph in 0G, but it's really meant to just let go of the telescope and push the two components apart. But given that it went and sprung open, it caused vibration within the telescope. So they had to understand, was that level of vibration greater than the vibration it's going to be subjected to during the launch? And that's what took them a few days. But the media release was, oh, we have to check it to see if the vibration damaged the telescope. They put the telescope through a couple of forms of vibration: launch simulation vibration and acoustic vibration simulation. And the telescope passed all of that. So if it could survive that, a little spring from the collar is not going to induce that much. They just wanted to make sure. But really what they wanted to do is make sure that the collar doesn't spring open when they don't want it to, and does spring open when they do want it to. So they took a few days and they figured out, whatever they fixed is the best way to describe it. So it's gonna, current estimate is to launch no sooner than Wednesday, December 22nd at 7:20 a.m. Eastern time. Now I say ET or Eastern time, because that way you don't have to figure out the whole daylight or standard stuff. It's just the current time.
Hopefully.
Yes, it's going to be launched from French Guiana in South America.
I would love to go.
Heat, mosquitoes, you don't want to go there. Okay, that's James Webb. Okay, we got to learn a new word, Gangatri Wave. So this is a new term. No, you're not supposed to know it. You can't look it up on Wikipedia yet. They were measuring the intensity of gas filaments in the Milky Way galaxy, and they found this very feather-like filament of gas that went between two arms of the Milky Way galaxy. Now, one might say, well, if you're a barred spiral, shouldn't you have those normally? Oh, but they found one in a different place. So this was found using the Apex telescope at Atacama in Chile. And they measured the energy level of the excited gas molecules, and they traced them across from one arm to the next. And so it's a, hey, look at what we found. Oh, we've never detected those before. Well, you get to name them then. So that's where the word Gangatri Wave came from, is the folks that came up with this. It's a research team from Germany, France, and the UK. And they named it after, scroll down here. The research named the formation the Gangatri Wave, an homage to the massive glacier whose melting gives rise to the Ganges River in India.
Okay.
So that's how it got its name. You know, if you're the first to find it, you get a say in what it might be called. Of course, if it's an astronomical item, there's always that pesky International Astronomical Union, and they get final say. Just ask Mike Brown.
Yeah, and then they're gonna name it Big Wave.
That's true. They're going to name it something stupid like Feather Wave or Big Wave, and they're going to remove that name from it. But it'll always be known as a Gangatri Wave. Still, it could be called worse. For those of you that have heard of them, neutrinos are these particles that come about as of nuclear fusion, like a star, like our sun, and it produces huge quantities of neutrinos, and they don't interact with anything. That's why they're called neutrinos, like neutral. You know, probably tens of thousands of them are going through your body right now, and you don't even know it because they don't interact with anything. But they've said they've detected neutrinos at the LHC, the Large Hadron Collider over in Europe. And I said, how do you detect something that leaves no signal? You know, you can't detect them on your analog to digital converter because there's no material that will produce a voltage based upon a neutrino passing through it. You know, the way you detect infrared light is you have a material that takes the infrared light, absorbs it, converts it to an electrical signal, and then you use an analog to digital converter, an ADC, to convert that to a digital voltage level. And now you can say, hey, my sensor detected infrared at this high in amplitude, this much energy. And that's how you say, we've detected this particular, you know, signal. But for a neutrino, there's no material that will produce a voltage such that you can use your analog to digital converter to say, hey, we've spotted a neutrino. The Large Hadron Collider, in some parts of it, produces lots of radiation. And the radiation has to be shielded from people. So they have dense blocks of material. And when they took out some of this, because you know it degrades over time with all the radiation, so you have to replace them. And when they replaced them, they went back and analyzed them, and they found 6 little tunnels, microscopic tunnels, that had been carved into the material. And they said, ooh, that must be neutrinos. Okay, that goes against the actual definition of a neutrino as something that doesn't interact with, as they call it, baryonic matter. So I'm waiting for another collider to say, we've also discovered neutrinos via the same mechanism. we took our radiation shielded and we sliced into it and found these little like microscopic snail traces that say, oh, we were hit with neutrinos. But there's no actual signal from a neutrino that says, I did it. So it could be some other particle that's doing this that left its traces in their shielding material. So put a push pin in this one. Let's see if somebody else claims the same thing. But neutrinos are described as elusive, but there is one kind of neutrino that is even more neutral than other kinds of neutrinos, because neutrinos get different colorings or different classifications based upon the energy level of the neutrino. And there's a neutrino called a sterile neutrino that, well, it could be that kind of neutrino or it could be this kind of neutrino, but it's supposed to start out as neither one. And then at some point along its path, it can flip back and forth to the other kinds of neutrinos. That it gets into a whole physics thing as to when neutrinos are traveling outward from the star they were emitted from. If you sample them at distances from the star, you'll find the same neutrinos are different colors at different points along the path. So they flip. And the only way that they can consider this flipping action to actually take place is if you have another kind of neutrino, a sterile neutrino that starts out as sterile and then toggles back and forth. So, but that's neutrinos in a nutshell.
But they interact with photons.
They don't interact with it. They interact with material, and the material produces luminescence, and what's actually detected is the luminescence. But
it's like when a neutrino hits a photon, you can actually see the, photon emission from, the collision.
But that's indirect. There is no way to directly detect it was a neutrino that produced that.
No, you cannot detect directly.
It's a supposition. It's a supposition by those who want millions of dollars to say they detected neutrinos, to say it produced phosphorescence in our 500,000 gallon pool of sterile water, purified water. And we buried it in a vault underneath the Atlantic Ocean. And therefore, the only thing that could have done this is the neutrino that passed, all the way through to the bottom of the Atlantic Ocean, through our metal cylinder, actually through a rock that is around the outside of the cave that holds our metal cylinder. So they're presuming that the only thing that could get there is a neutrino. But yes, they're detecting what they believe to be neutrinos based upon the photons that the water puts out when a neutrino supposedly interacts with the water. Now it's a very, very high, very low probability. So if you have 500,000 gallons of water, you might get one of these photons out every few years. So, some might also say, well, that's just noise in your sensors. Neutrinos, they're very elusive. And for those of you that thought Russia is leaving the International Space Station, well, apparently not soon. They just added a new docking module to the space station. Now, why you need another docking module when you already have two, I don't know. Maybe they're changing something on the Russian style connectors. But they added a 5-ton docking module called Prichal to the International Space Station this week.
Maybe it's a lifeboat for all the junk they have decided to blow up.
No. If you look at the picture, the thing on the back, this part right here, that's the spacecraft. That's the capsule. This thing on the front was mounted onto the front of the capsule, and that's the docking chamber. So this ball will connect into one of the mounting points on the International Space Station Russia module, and that will add, see the holes on the side? They can actually dock multiple spacecraft onto there. So, I probably docked up to 4 spacecraft onto there once they connect it in. I don't know why they'd want that many spacecraft docked at the ISS, but so far there have not been any inadvertent rocket thruster events. And so far, there have not been any detected air leaks from any of the Russian modules, but we'll see. So a couple of weeks ago, I announced that NASA had launched Landsat 9, one of these, multi-ton satellites that they put up in geostationary orbit. They're supposed to last about 10 years. And, they use them for Earth observing. They might be observing sea level or foliage on the ground or volcanoes or any number of things. Landsat is the latest one. And so, of course, it sent back pretty pictures to prove it was actually up there taking pictures. And you can actually see the waves on the surface of the ocean. This is actually in Lake Michigan, I think. So extremely high resolution.
Nice.
It's, when you launch one of these things, you design it about 5 years in, and then you launch it to last about 10 years. So by the time it's at the end of its usefulness, it's about 15-year-old technology. So if you think of the previous Landsat, it's probably 20-year-old technology by now. So just boosting this by 5 to 10 years in imaging technology is dramatic. So you can see waves on the surface of the water. Let's see, this one is in the Himalayas. You can, over time, if you photograph the Himalayas again and again from the same spot, you can actually see the retreat of ice on the mountaintops. And the Florida Panhandle, you can actually see sea level rise occurring in bays like this, inches per year. And since it's multispectral, it can do things like, let's see how the plant life is doing. So you can monitor pollution levels, you can monitor growth levels of forests, and watch for all that stuff. So I'm happy that Landsat's up there, but when somebody says, that SpaceX has large satellites and thousands of them, they ignored things like the Landsat satellites that are going to be up there for 10 years, and they're in geostationary orbit. So even at the end of their life, they don't actually bring them back down. They just slide them over into a parking orbit somewhere over the Pacific Ocean, the Atlantic Ocean, or Siberia. But I'm happy they're up there. For anybody who's played with a green laser pointer, unless it's a very, very new one, the laser that you're working with is actually an infrared laser. It takes the infrared photons, runs through a yttrium aluminum garnet crystal. It's kind of a yellowish looking crystal. And that crystal does a wavelength change on the photons. So instead of the photons being at, 1,000 nanometers, they go through this crystal and they come out at about 550 nanometers, which is green. So that handheld laser inside is actually taking the infrared light and converting it to green light. Well, they're finding out that if they change the chemistry of the crystal, they can do a frequency doubling to make more efficient conversion of infrared into visible, which increases the energy per photon, which allows you to make more efficient solar cells. So you've probably heard of Perskovite solar cells. That's a new kind of a solar cell. It's a lead crystal. It's a leaded crystal solar cell. But they take a broader range of wavelengths of light and can convert it to electricity. So the particular solar cell itself is not getting more efficient. The conversion process is what it is, and it converts, probably 19 to 20%. But the way they get up to like 28% overall for the solar cell is by taking in a broader range of light, a little bit of infrared, a little bit of ultraviolet, and then they use frequency conversion to shift up or down the photons to make the photons wavelength more in keeping with what the dominant wavelength is of the solar cell. So that's how you make a solar cell that can convert more of the sun's available light into electricity. Is not by changing the process of the conversion, but by changing the light itself to be more aligned with the most efficient range of photons for the solar cell. And while we're at the world of quantum physics, this I found a little, I did not know that kind of thing. You might have heard of Samsung's latest generation TV sets that have quantum LEDs, quantum LEDs in them. And
Nope.
the idea is if you make a little container small enough, then you can put certain chemistry polymers inside there. And then if you apply an electrical field to it, it will produce light. Now you can take the same chemistry polymers, and if you make the size of the container a different size, it produces a different wavelength of light. So if you want red, green, blue, yellow, whatever color you want coming out of your pixels of your TV set, you can have different colors with a single chemistry, and all it does is it makes different size wells to hold the little dots. Now, in a TV set, there are many thousands of molecules of these polymers in each one of the quantum dots, and there's hundreds of quantum dots per pixel. This is why when you look at quantum dot TVs, you go, I'm 2 feet away from this thing and I don't see any pixels. That's because the dots are microscopic. The actual domains that hold the molecules of the dots, those are nearly microscopic, and they pack a lot of them in to each area where they want a pixel. So it literally just makes all the pixels flow together. So that's why you get these lovely images. But if you look at the individual dots themselves, they don't stay on full time. You can apply an energy field to them, and sometimes they will come on and stay on for a while until you turn the field off. Sometimes when you turn the field on, they'll come on and then almost immediately go off, and then they'll come back on again. Well, if you didn't have so many of the dots in each one of the pixels of your TV set, you would actually notice that the individual molecular dots are blinking off and on as long as the field is applied. But there's so many of them, you don't even notice it. But if you're dealing with very, very small particles and you're trying to excite materials or bacteria or viruses by a particular wavelength of light, you want to have the thing holding the quantum dot to be 1-to-1. So you want to make the container to be just the right size for a nice single color yellow. And then you apply your field and out comes the yellow light, and then it goes off and then it comes back on again. So you want to stop that. And what they found was if you take an infrared laser at very low power and you pulse the dot for not nanoseconds, but femtoseconds, that's like, thousands of billions of a second. You just sort of give it that little nudge in infrared. Then when you turn on your field, it'll actually stay on when you have the field on longer. They didn't stipulate how much longer, but the funny thing is they don't really have a confirmed explanation as to why it does what it does. And they don't have a confirmed explanation as to why it stops doing what it's doing and for how long it does it, because none of that's currently predicted. It's just so weird to think of it as they had these quantum dots that were supposed to produce a particular wavelength of yellow, and they turned them on, and then they started randomly blinking. Not always blinking, not blinking for a specific period of time or being off for a specific period of time. They would just weirdly blink. And somebody thought, what if we just kick it with an infrared laser at low power? Oh, look, it stopped blinking. And now they're coming up with sort of the backwards science of why this happens and why the laser does this. And it's almost, this is weird. It's almost like, think of an electron as a piece of dust on the lens of a very small diameter light. The electron disrupts the ability of the photons to come out of the quantum dot. And by popping a laser at the quantum dot, it kind of shoos off the electron, and now the quantum dot will come on and stay on for a longer period of time, at least as long as you want the field turned on. I just think that's like really shooting in the dark with the physics principles there.
Yeah, learn.
Basically, it's like a science. So you're searching something, you discover something, and then later on you discover why.
Yes, but think about it this way. What kind of an instrument would you need to confirm that it's one electron disrupting one quantum dot?
Yeah, you
How
need
it
to make
starts, what is it that makes the electron hang there? Because there's a relationship between photons and electrons, but
And then
only
you
in the
remember
presence of
when you're-
atoms.
and then you remember when you're in quantum states, even observing changes the problem.
Yes, that's
So
the other
it's
wacky thing
gonna
about
be very difficult to know why.
quantum physics is if you perform an experiment and you have a certain result, and then you go back in and you put a sensor in there to try and understand why it's happening, it will change the way it behaves. So if you ever look at the double slit experiment, if you do this on a quantum scale, if you don't observe the double slit experiment with instruments, it performs its usual double slit behavior. The moment you put a sensor in there to try and understand why the photons are moving in the direction that they move, the results change. You don't get the traditional, very obvious double slit result. Yeah, quantum be weird. Back to my weekly gripe about the Hubble Space Telescope. So I saw this. This is newly released this week, November 26, 2021. Hubble spots Herbig-Haro object in NGC 1977. Hey, that's a really great image from Hubble. When was this image taken? They've actually gotten smarter because I detected this the last time. Hey, the article came out this week, but if you look at the caption of the image, it says, oh, well, we took this image back in September. They've now removed the image dates from the pictures. So you can't tell when the picture was taken.
Oh, sneaky.
Yeah, I just think that's so clever of them. But you look at the image and you find out, oh, which instrument took the image? Well, it turns out there's a particular camera used, and that camera is not yet once again operational on Hubble. See how highly magnified this is? And it's a very dim part of a nebular cloud. But if you were to go in and say, what is the current operational status of Hubble? You'll find that the Wide Field Camera 3 just recently became operational again on November 21st. And the Advanced Camera for Surveys, another wide field camera, was operational again on November 23rd. And the anomaly happened on October 25th. So how did they get this high resolution narrow field image? Well, it certainly wasn't with the two wide field instruments they've currently got operational again. So taking the dates off of the images, but leaving on, oh, by the way, this came from, a particular camera on board Hubble, and it's not the wide field and it's not the ACS camera. Oh, well, that wasn't taken recently. So there's another thing that NASA's going to have to figure out is if you've got smarty pants like me out there going, you didn't take that with one of the two instruments that are working once again. You took that a while ago, didn't you? So that's the next thing they're going to do is they're going to stop telling you which instrument they took the picture with. Yeah. Okay, so that is the news. Any other news items that people might have
I
come
have a
across?
question about your last thing, your last piece of news.
What's that?
Well, you've very well explained your Sherlock Holmes ability to tell when it was taken. But is it a political reason or a money reason, or why
No,
are they hiding it from the general public?
It's a saving face kind of thing. At
It's
the moment,
like if you stop putting pictures online, people stop clicking on it, and then you stop funding, and people lose the
Yeah, so
interest.
it's money.
well, it's
Gonna stop the
it's
mission.
it's a worse roll forward than that. If you did not periodically see stuff from the Hubble Space Telescope, and the last thing you can read about current information is it was broken, you would think, oh, it's at the end of its life. Let's just, burn it up and stop funding it because it's broken. And
Yeah,
how are we going to service it? So as long as the last thing you hear is it was having a problem and you don't see any new pretty pictures from it, people are going to come away with the false impression that it's not worth continuing. And as soon as the James Webb Space Telescope gets launched and becomes operational, it'll be, why do we need to spend money on Hubble anymore? And they will be completely clueless as to Webb is only infrared and Hubble is infrared, visual range, and UV.
okay. So you have explained to us that you can tell that they've shut down, and you've told us why they probably have done this. It's a money reason, really.
No.
No,
They haven't
it's
shut it
broken.
down. They have not shut it down because they're short of funding or they want to save money. It's literally a technical issue. And I think at some point they're going to realize, oh, we just have to flip over to this backup that's already there in the telescope and it fixes the problem. But in the meantime, they're doing it one instrument at a time. They've got the general purpose computer working again. They took an instrument that was turned off for 10 years and they tried some things out on that and they found a way around it. And they tried to do that for one of the other, let's just say, less critical instruments aboard Hubble. And after making further modifications, they got that instrument working. But what that told them was there's no one simple solution for this. You have to maybe come up with a solution in software that might be different for each one of the instruments, the timing of them. And
Right.
they now got two of the instruments working again. So it's not a matter of saving money. It's more a matter of letting the general public believe that Hubble is fully operational when it isn't, because they don't want to give the false impression that Hubble is broken beyond repair at this point.
I know you heard saving money, but that isn't what I meant for it to be
Okay.
said. I was saying that it's a money issue. I wasn't saying about it being saved. What I'm just saying is they're hiding, they're not coming straight forward and saying, we're having some issues, it's taking us some time to get it back loaded. Now you generally let us know that this is not how you would like it presented, but I wonder how they could meet both goals, your goal of being more forthcoming and the goal that they wouldn't lose money, because I see their point that if they're not producing stuff or appearing to be working, that it gives them a harder time. And I just wondered, is there a happy ground to do both?
If you depend from the public, no.
I don't think so
The-
either. I don't see
the-
how they could make you happy, Monroe.
The public sees what is put in front of them. I see what I have access to. So whenever I see a public pronouncement of, hey, look at this pretty picture from Hubble, I look at it, I look at the data and I go, okay, I see what you're saying, but let's see what the current actual status is of Hubble. And if you know where to look on the NASA website, you can see that. It tells you plainly, yep, we had an instrument back in October, we had an incident back in October, and we've since got two instruments working again, one that we turned back off, and a third instrument that is now operational again, and we've got a few instruments left to do. So both statements are out there. I just wish that somehow in the look at the pretty pictures, they would include something about the current state of Hubble, because if it does come away with at least one of the instruments absolutely no longer functioning, they're going to have to tell the public that at some time. And if they keep it in the dark for too long before they, make a public pronouncement of it, it's not going to look good on the part of NASA.
Does it look like a cover up or something you're saying?
Yes.
Or-
Yes.
yeah. And how long do you think that window of time is available to them to look okay in the public's eye?
I'd say if the web space
They
if the
could
web,
do just like they did for the Arecibo. They go like very expensive to fix. There is no more funding. Now it's broken beyond repair, and then katabom.
Yeah.
So basically, they're gonna take the same strategy. They will try still while they're putting on data and putting pretty pictures and stuff. So it means that there is still a possibility to fixing it, doing, you know, programming and working around. But when is the point that it start to having lots of problem, NASA is gonna it cannot fix anymore. Let's verify if we can still funding the people to working on the problem. And then when it's get a point where that is no more way to fix, they're gonna start, you know, slowly trickle down like a receivable kind of thing.
So
well,
you
that's-
think it's
that's-
okay right now? You don't see it as being a problem, that it needs to be changed
don't
to the
know
public right
yet.
now?
I think
Right,
we
they
are in the
don't know.
phase, and I
That's
don't know.
transition. Yeah, we don't know.
What they are trying is not to lose the total funding until they're sure that is no more fix.
Yeah, and so I think that's okay, because if they could fix it, then that would be great. And if you could close it down before they got the chance to do that, that would be horrible.
it's all a matter of public perception. And every time NASA sends up, or even European Space Agency sends up a probe, they don't just put one instrument on it. They usually pack it as full as the weight will allow of instruments. And you know, if they have 6 instruments and 2 of them over a period of time become non-functional, it's still a valuable spacecraft. So if Hubble had 8 instruments on board, and 10 years ago they turned off the NICMOS camera, it was still a very valuable instrument. Well, NICMOS wasn't usable for scientific purposes anymore, but they could use it to check out data communications. So rather than potentially jeopardizing the working instruments, they turned on the instrument that they knew had certain deficiencies, and they tested out the data communications with that. So I think that the technical analysis and repair operations that they're doing with Hubble, that's just fine. That's great. I just think that if you hold out too long and you don't explain the truth to the public can be very resentful. Now,
Right.
when the Webb telescope is up and operational, the next time you hear that Hubble's had a problem, you're going to see clamor in the public to just stop doing anything with Hubble, because we've got the Webb now. What do we need Hubble for anymore? And every time Hubble has a failure, that's always pointed out that the Webb is the replacement for Hubble, and it's not. The WFIRST, which is the next space telescope after the Webb, is also not a replacement for Hubble, because both of those are infrared telescopes. So the best way to describe it is keep an eye out on what they're publicly promoting. But if you want to know the actual status of Hubble, you know, go to NASA or go to the Space Telescope Science Institute and get the actual facts of the matter. And they're there. I mean, you don't have to go looking hard for it. It's just, that's not going to be what NASA puts out in front of the public. Until it's back all operational again, and then they will shout it from the highest mountaintop. It's fully operational once again, except for NICMOS.
Which hasn't been functional for years.
More than a decade, yeah. It's functional, it's just not good enough. In other words, it's not getting a strong enough signal in its imager to be useful for science anymore. But it's still a camera, photons still come in, electricity still comes out the back, they can still get images from it. It's just not the best of images. But as an instrument, they can still use it as a trial balloon to get things working again.
Okay. Well, I have a feeling that if this continues every month, that you'll keep saying they should put it out into the public and let them know that it,
Yeah.
but at one point you'll get to a point to say, this is getting to be too late. They really have to do it now. to
Well,
let
remember,
public
remember
know.
this current failure happened in October. It was not a complete shutdown of the Space Telescope. It was a data communications fault that occurred once. And in the realm of NASA, if you detect something and it's not supposed to behave that way, it's cause to start an investigation program to see why it happened. Is it something that's going to recur? Is it going to cause a more severe problem? And how do we deal with this? So they're doing the right thing internally, and they are working through the problem. I just think they could put a better public face on it. Just a little bit of truth. It doesn't have, you can still put out the pretty pictures and say, look what Hubble did, and and say, we gathered it like they did initially. We gathered this data back in September for the grand tour of the Jovian planets, and but they removed the dates from it and any mention of when the image was taken. So if the general public sees a news release from Hubble dated in November, but it's instruments that were not operational since last September, and then later on you go, well, the instruments that took those pictures, they're not coming back online anytime soon. How come we're just now hearing about this? Yeah, that's not going to go over well with the public. But as far as spacecraft that are still considered valuable, even after we've lost contact with them for a period of time, we do that. Voyager 1 and Voyager 2 are right at the outer edge of our solar system. We still have contact with Voyager 1. We lost contact with Voyager 2 for almost a full year. And it was not because of anything that happened on Voyager 2. It was because NASA had to do some upgrades to the Deep Space Network antennas and receivers here on Earth in order to make certain capabilities available for the Webb telescope, specifically the X-band receiving and sort of upgrading the receiving antennas and supercooling of the receivers to better improve the signal to noise ratio, which would improve our ability to receive signals from Voyager. They brought the Deep Space Network back online, and okay, where is Voyager now? Well, obviously it's moving out. It didn't stop moving simply because you stopped listening and commanding it. It's continuing to move out. And so they had to relocate where Voyager was by listening for it for a while. And then once they heard the signal, they knew, oh, if we listen to it and we find it, on a couple of successive observing sessions with the radio telescopes of the Deep Space Network, now we know its track again. Now we can follow it. Now we can command it again. And they restored communication with it after not being able to talk with it for 2 years. But the number of instruments currently running on the Voyagers is a small number compared to the original quantity. You're not going to receive any pictures from deep space because that consumes too much power and it takes too much time to deliver all the bits of the megapixel image back to Earth. Remember how when you're communicating over longer and longer distances, the rate at which you can send bits, how wide the bits have to be to overcome interstellar noise is such that you don't get gigabits or megabits or kilobits. It's seconds per bit. So all they have running is some numerical data detectors. So it can detect magnetic fields and it can detect electrical fields, and it may be able to detect certain types of ionization. And that's about it. All the other instruments are shut off to save power because the radioisotope thermoelectric generators are not putting out the power they once did, 50 years ago. So they have to conserve power. And the way they do that is they turn off instruments they don't need. But Voyager is still valuable because it's telling us what is I guess you could say, what is the deep space weather like beyond the edge of our solar system. So they're still valuable. And I think Hubble will wind up being the same thing. As long as the main computer and the main power supplies continue to function, or they have backups on board for them, they'll have a certain number of instruments that will continue to operate. And as long as at least one of those instruments produces pretty pictures, I think Hubble will still be in the minds of people. But the moment it gets down to just data, people will long for the pretty pictures. And if the web is producing pretty pictures, why do we need Hubble anymore? Yeah, I know how the public and in particular Congress acts towards funding and getting people to work on these projects. And Hubble has given people careers, not just a job for a few years, but actual careers with NASA. So
Yeah. And
at
the
some
other
point,
problem, yeah.
at some point, Hubble will be not operational or will burn up and be no more. We thank it for what it's done in the interim.
Yeah. So one of the problems is that, like, when it's just data, is still super valuable. When Congress is not aware of it, people is not defending it. It's like the one that it's paid by people. They donate money for it. It's like very little state funding for that. And when it gets to the point, they say, nah, let's just burn in the atmosphere, something out of it. And the other thing is that when it gets a point that's no more pretty pictures, they will stop the funding. People who donate for the telescope is going to dwindle. That should say thank you for all the people who actually still working and fixing problems, because I think 5 years ago it's been working way much more than my problem.
The Hubble space, not exclusively by the National Science Foundation. The National Science Foundation gets a fixed budget from Congress. And if any of the agencies under NSF want to do something new, have a new spacecraft or a new telescope or a new radio receiving station, they don't get additional funding for that. It's tell me what you're going to turn off or deorbit or not use anymore to get yourself the funding to do your new stuff. So it's kind of fixed based funding for things that are science. That's, maybe it makes sense to some people, but not to people doing the science.
Space Telescope Science Institute.
Yep, STSCI. But if you look beneath the covers, you'll actually SF. There's all kinds of operational fingers in those pies. So last week's presentation of solving space junk is available on the YouTube site in case you missed it. December 4th, next Saturday, William drives, and that one will be specifically photonic propulsion. And you might say, well, I've heard you jabber on about that before, but last time we did this, there were a couple of things that came up as, well, what about this? And how does that affect it? And so I went in and did the study and found ways to deal with those or to mitigate them. So that's really what it's about, is just improvements in the understanding of it. And remember, these things are put out on the public YouTube site. So if anybody looks at the first one and goes, yeah, but what about, and then later on they see an update that says, yeah, I got that covered. Maybe it gives it, as the saying goes, better legs. So on December 11th, we'll still do the James Webb Space Telescope presentation with our subject matter expert, Dr. Will, from the Space Telescope Science Institute. In order to make best use of Will's time, we won't have a news segment next week, but following the presentation, we can still do our ad hoc discussions. And if there's anything that comes up in the news, we can ad hoc discuss it then. As I said, the launch of Webb has moved to December 22nd. Now it says 7:15 there, but I know the actual launch time is 7:20. I don't want anybody to tune in at 7:20 and see that it launched 20 seconds ago. I'd rather they tune in 5 minutes ahead of time and see the last few minutes before it launches. And there will be no online sessions on Saturday, December 25th or Saturday, January 1st due to the seasonal holidays. So enjoy your time off if you're not retired like I am. And tonight we're going to be talking about the lens cameras for astronomy and how to control permanently mount on the outside of my house, so that ad hoc I could have it pointed stuff and you don't have to go out and grab your telescope, set it up on your tripod, do an equatorial alignment and all that kinds of stuff. It's kind of like having your own astronomy observatory to get into and to hold a large telescope. This is the very roof of my house. So we had a presentation on this a couple of months ago, and I've since moved the bar, so to speak, on how the software is coming along and the things that I've been finding out. that I have to tend to, the stumbling block, so to speak. And so that's what this update's about. So wherever you see the big red update or red font, that will be the things that have changed since the last time. So in order to avoid boring everyone with all of the technical minutiae that they heard about a couple of months ago, we'll just skip over those.
We're
unless
never
somebody has a
bored.
question. Okay.
Tough crowd.
Okay, so the idea of doing this is to be able to have an app satisfaction. So if you could just say, hey, what's the sky look like right now? Well, I've got surveillance. If there's something there in the west, let me fire up the astronomy camera because it's online on my point there. And oh, look, that's Jupiter. Or oh, look, the moon looks matter of a couple of minutes to go from what if to what am I looking at? That's the idea. And it's all based upon the surveillance cameras have come way down in price. They used to be like $1,200. Now they're more like limited capability. They'd have, you know, a 1 megapixel imager in them. Now it'll do a variety of exposure ranges under software control. It does wide cool. And since it's meant to be outside, it's a weatherproof enclosure. Although we do flip it upside down and put glass on the outside of it. You don't have the same sort of USB frame drop directly onto your laptop. And there are standards for doing this. And there are standards for doing astronomy software to what I'm needing to do is to create the bridge to map between two standards. And I'll show you some stuff on that. So this is what the camera looks like. So it fits inside my mitt, inside my fist. And you can see it's an 84 millimeter aperture, but think about your mobile phone. Small and takes such good pictures when it has such a small, so the focal length of the camera in your phone, the camera has so many megapixels in it, and it's to these pan-tilt zoom cameras, is they've taken the camera technology from high-end mobile phones and put it inside pan-tilt zoom surveillance cameras. But you have to cobble together some components because the camera doesn't speak directly to a network connection. See another circuit board. So you see on the inside here, this circuit board on the back, that's actually the network interface processor. And then this circuit board on the side is for controlling the pan-tilt zoom cameras. And the actual circuit board for getting images, it's hard to see, but it's the inner layer board is actually the one that captures the images. So there's actually 3 circuit boards inside this tiny camera. And it produces a lot of heat, and there's actually ribs on the top of it to let the heat dissipate. But if you see this much electronics and this much capability in cameras that are this high resolution and low light, and it's $250, you've got to ask yourself, why am I paying $700 for an uncooled astronomy camera? It doesn't even move. It doesn't do zoom. It doesn't do automatic focusing. It's just what the market will bear. So here's the first standard we come across, ONVIF, the Open Network Video Interface Forum. A group of vendors that produce products in their surveillance camera marketplace came together and said, wouldn't it be nice if we all spoke the same language, if we could all interface the same way over networking, over the internet, basically. So they came up with this standard called ONVIF. Great. You can now write software, client software, to talk to a variety of different brands of cameras using the same capability. So concepts like pointing the camera, sort of rotating it and tilting it up and down, zooming in and out, focusing the lens, adjusting the exposure, the processing, all that can now be done digitally. And you can do snapshot imaging, or you can do video stream imaging. You can capture videos. So these work over wired or wireless. I'm going to be using wired because that's much more reliable than wireless. And for those people that might understand a little bit about data communications and computers, we're actually be using the SOAP protocol. This is something Microsoft came up with years ago. Simple Object Access Protocol. It uses XML over HTTP, over TCP, over IP. I know it's a lot of gobbledygook, but the people that know what I'm saying go, oh, I understand now. That's the first standard. Now we've got a standard ONVIF for interfacing to the camera. Now we've got to have a standard on the other side for astronomy applications that do like planetarium and imaging to talk to telescopes and cameras. And that's where this other standard comes in called INDI, Instrument Neutral Distributed Interface. It's an open standard. It's basically a bunch of software engineers that do astronomy stuff that got together and said, let's come up with a standard. And they did the same thing. Completely different standard, not directly compatible with ONVIF. It's not meant for the same purpose, but you can create something that will be the glue that takes, requests from INDI and maps them to ONVIF. And now you have a surveillance camera that behaves like a telescope and a camera. So INDI also works over wired or wireless Ethernet. Here's another similarity. INDI is XML over TCP over IP, and that also works over the internet. So you have two kind of similar protocol techniques, but they don't speak exactly the same words and phrases and verbs. So you need something that will glue the two of them together. And that's the hard stuff that I've been working on. So ONVIF to INDI protocol mapping. So we need something that will take astronomy software like planetarium, imaging, and video capture and convert, that will talk INDI. And now we need something that can receive INDI requests and convert that to ONVIF. So that's the drivers I'm working on. So I need a driver for telescope mount. I need a driver for focusing. I need a driver for the pan, tilt, zoom movement, imaging, focusing basically, and another one for actually capturing the image of the image captured by the camera or streaming video for video processing. So this is the glue layer that I'm working on, and it's not just one piece, it's like 6 pieces. So from the last discussion, I had already mentioned, yep, I'm going to need a telescope mount and an imaging camera, and done. And then I realized, oh, wait a minute. Cameras are not focused in astronomy. The focuser is something that's an add-on to your telescope mount. So whenever you command your telescope mount, you might have your hand paddle to command your telescope, and that's where your focus controller is. Or your astronomy software that does your planetarium positioning of the telescope mount, that's where you tell it to focus. And there's some fancier ones that bridge the two, and the focusing can actually be done in the image capture software. But you've got to have a driver for it so that the focusing can work either with the telescope mount or it can work with the imaging. So that's the idea. As to the software, I should not have to write any application software to drive this or test it. There are pieces of software, you probably have heard of Stellarium. It's a planetarium simulation. It makes a picture of what the sky looks like from wherever you're at right now. And then you can click on objects and it will center on it. And then you can select the menu item that says, connect up a telescope using INDI, and now make the telescope point at that thing. And it will get you generally in the vicinity, it'll appear in your field of view, but then you want to nudge it. You want to move it up, down, left, right to kind of get it in the center. And now you can take pictures. So there are pieces of software called Stellarium and K-Stars and Carte de Ciel that talk to INDI. So unlike ASCOM, INDI will work on a number of different platforms. So INDI works on Windows, INDI works on Linux, different flavors of Linux. So it's more open than ASCOM. So the actual drivers, what do they have to deal with? In the case of the ONVIF side of things, side of the driver, if you've ever looked into ONVIF, you'll understand that it has these things called profiles, and the profile says what commands you can send to the camera to do what kinds of stuff. The A, G, and Q are for things like accessing it for secure access to the camera and for making network connections. If you look at the S profile, you'll find that that's the part about doing video and adjusting the position, the pan, tilt, zoom part of it. But then if you want advanced video to be able to adjust the parameters or do snapshots, that's the T profile. So that's the ONVIF part and what you have to talk to. And then within INDI, you have a bunch of different kinds of drivers. And we have to do a telescope or mount driver, an imaging camera driver, and a focus driver. And then I have a common library that takes the INDI stuff, maps it to subroutine calls to do ONVIF stuff. So this is how it all plugs together, sort of the wiring of it all. You have the internet. They're on the left, the internet router, so you can remote command this thing if you wanted to. You have your application computer. That's your laptop running Windows on which you're running Stellarium. Then you have a Raspberry Pi computer. Of course, I have to have a Raspberry Pi. You have the Raspberry Pi computer on which you're running the INDI server and the drivers. And then they talk over the network to the camera. But the camera needs power. And you can actually run the data to the camera and the power over a single Ethernet cable. That's called power over Ethernet. Now, the INDI server computer, for those people that might have played or seen a Raspberry Pi computer before, this is it's about the size of a playing card. And you can get one of these things with the power supply and the interfaces and stuff like that for under $100. And it will connect up to your network. It has the ability to connect up a TV like an HDMI out. You can hook up a keyboard and a mouse to it, make it a real computer. But the idea is we need some kind of brain to run the INDI software, and INDI works better under Linux. So that's why we have a Pi running Linux. That was the hardware interconnects. And now you have the software interconnects. So on the left, you have the application computer that's going to be running Stellarium. And then over on the right, you have the INDI server computer. And then in the middle, you have the actual camera itself. And the camera actually has multiple computers in it, for doing the pan, tilt, zoom, and the networking and the imaging. So it's got microcontrollers in it. There's 3 of them. But these are all the computers. And then the blocks inside the gray areas are these software components that have to talk to one another. And if anybody's ever taken a look at INDI, I don't know that they have, but that's why I put it in the presentation, is because once I put this video out there for public consumption, somebody will say, hey, I know INDI, how does all this work? And this is the big picture of what is known as the object class libraries within INDI. So you have a CCD camera, that's the actual telescope camera. You've got a focuser, and you've got the telescope mount. And those all talk through common interfaces like a guider, a focuser, and a telescope. And those appear as collectively a default device. This is just a generic device under INDI. And then there's a common set of commands for connecting up the network stuff and things like that. That is the base device. So that's how it all shapes up under INDI. So typically you'd think of an interface device as like a RS-232 serial port or a USB connection. This will actually be over a TCP/IP network connection. And there'll be 3 drivers: telescope, CCD, and focuser. Or CCD is camera. And telescope is actually mount, because there's no telescope. The camera and mount is all one. And you have to be able to connect and disconnect to it. And there are certain parameters associated with each one of these device drivers. And you have to be able to command them to do things. And if it's a camera, you got to be able to take pictures and video and adjust the exposure. In the case of the focuser, you have to be able to move the focuser in and out. In the case of telescope, it's, you give it a coordinate, a right ascension and declination, or an altitude and azimuth, and it commands the camera to slew to that place. And then you can nudge it to be more in the center of your field of view. So all of that stuff has to be working before you're going to get Stellarium to move it to where you want, and then the software to take pictures. And there's just a little more detail of that same sort of thing, breaking it down to levels of what you have to do. It's little things like a telescope. You have a telescope mount. Well, what are the kinds of things you have to do with it? Well, you have to be able to park it and unpark it, which says, make the telescope go home and shut down to park it. And then when you first set it up, you have to unpark it to bring it into its alignment position. And then you have to be able to slew it to an object given coordinates. And then while it's doing that, it's moving. So you have to know the status of it. And once you get it on target, it has to guide. So as the Earth rotates, the camera has to continually nudge itself to track the planet or the moon. Has to know where it's currently pointing. Has to be able to set its shutdown, its park, its home position. And then if things get out of alignment, you have to be able to say, trust me, I know where it's pointing and it's pointing in the right place, or it's synchronized. The camera, you have to be able to capture images or video. You have to be able to set the exposure. In the case of streaming video, you have to be able to say, start taking the video, and then after a certain period of time or on command, stop taking the video and store the file out there. And the focuser has to be able to move the focus in and out and say, I've got the focus where I want it, synchronize it. So it has to do those kinds of commands. So here's one of the first hurdles I ran into. If the camera is inside of a glass dome and the camera goes, oh, it's dark outside, I should turn on my infrared illuminators so I can see in the dark. And it's doing that inside of a glass dome. The infrared light's only going to get as far as the glass dome before it reflects back inside the glass dome and distort your image. So I had to find a way to turn off those LEDs, even though the camera's going, hey, it's dark, I want to turn on my LEDs. In the ONVIF standard, there are ways of doing that. They're called lamp on and lamp off. Well, I found that the guys that implement the cameras don't really follow the rules, and they came up with a different way of doing it. And so many people followed their different way of doing it that it became part of the standard. So I had to research that and go, why for do you do it that way? And here's what I came away with. Lamp on and lamp off don't give you enough flexibility. And they don't actually say what the operating mode of the camera is. It just says, turn the LEDs off and on. Well, the camera operates in two exposure modes, nighttime and daytime. In the daytime, it knows to turn the LEDs off. At night, it knows to turn the LEDs on. So that's what it's thinking about, is not LEDs off and on. It's thinking about night mode, day mode, or automatic night and day mode. So it has these three presets. So I had to make changes to my software to say, okay, when I fire this thing up, I want to put this sucker in night mode. But only if I detect it's post-sunset, it's dark. Because in the daytime, I want it to change the exposure automatically, because you can take pictures and video of the moon in the daytime. And if I find a way to put a solar protective filter on this, I might even want to take pictures of the sun. I might want to do an analemma. So you have to get the minutia in there. Focusing. The camera, as it currently stands as a surveillance camera, wants to do autofocus. The way autofocus works is it judges the brightness of the thing you're pointed at, and it adjusts the focus in, out, and it detects the brightness of a large blob somewhere in the focus range. And as it narrows that down to a brighter, smaller area, it says, I'm in focus now. Think about this for a moment. I want to take a picture of some craters on the moon. I'm not going to be looking at the entire moon. I'm going to be zoomed up into a large, bright area that's got, not very dark things. So the camera is going to struggle to do autofocus. So I want to disable autofocus and either let the astronomy software or let the operator tweak the focus. So I had to find a way to turn off autofocus. And they didn't make it easy for me. The only settings you can do in the ONVIF standard is you can turn off autofocus until you next move the telescope, which that's kind of disheartening, because if I move the telescope to my celestial target and then I have it tracked, every time I move it, I've got to turn focus back off. Welcome to reality. So I have to have a way to turn off focus, and then just adjust it when I need it. And then home. I want to be able to have the astronomy software arbitrarily set home. And that's different than setting the home position of a surveillance camera. On a surveillance camera, you typically make the home position a protected direction. So if you've got a camera hanging underneath an eave, you'll want to turn the camera around so that the lens faces the wall, so that it's better protected from vandalism or bright sunlight or bright lights. And when you turn the camera on, it'll do its little self-diagnosis and swivel around and then point at a certain direction. And you want that to be its defined home position. So I've got to be able to do that. And that will actually be in the driver. That won't be in the camera itself because I can't rely upon the go-to home position in less expensive cameras. Positioning. Think about it this way. If I have a surveillance camera and I want to tell it where to go, where to point, I'm going to give it maybe a compass direction like point west. And it's going to be a wide field view. So it'll get you in the ballpark of west. It's not precisely west, it's in the ballpark of west. And then you will zoom and move and zoom and move and zoom and move until you get down to what you want to see. You'll have coordinate-based positioning that I have to test the camera for. So when I first fire up the drivers for the camera, it'll have to do like a 360 to know where all the positions are and how fast to move the motor to do a 360. And then it'll have to do a horizon, 0 degrees, vertical, 90 degrees, and then go back down and go, okay, this is the range. And now that I know the ranges, I can then say, do you want to move absolute? Because I now know the degrees in any direction because I know the total range. Or do you want to make a small increment at a certain speed, a certain slew rate, up, down, left, right kind of thing. And the driver that maps it all, the INDI side of it will receive the traditional astronomy camera commands, and then it'll translate it in an OnVIF mapping library that works for all the different drivers that are INDI to OnVIF, and it will map it to the underlying commands I need to tell the camera. So it'll hide all that beneath the surface. And I have to get all of this right such that it's pleasing or satisfying to amateur astronomers, which ain't easy, so no pressure there. And in case you forgot what it's going to look like, it'll be mounted up on the apex of the roof of my house, but it'll be inside of a dome like this. And the white big band there is a weather strip. It's actually just multiple layers of very, very thin styrofoam, the polyethylene styrofoam. It's not hard styrofoam, it's soft styrofoam. And because the thickness of that foam weatherproofing changes with temperature, as the day goes to night to day, I'll have to actually put a bead along the bottom side of it to keep the glass dome from sliding up and down as the temperature changes. Now I had to make sure the dome was a bit larger than the camera so that it could move around freely in azimuth and tilt, and then make it large enough in headroom so that the heat produced by the camera can hang out in the upper part of the glass dome and radiate through the glass to keep the camera from frying itself in the daytime. And when you think about South Florida with its high humidity, I needed some pressure valve to release the humidity. And so that's why this is multiple layers of polyethylene bubble foam, fine bubble foam, and so that the water vapor can release itself. And the heat in the top can act actually like a dew heater to keep the entire camera at a certain level of heat to keep the dew out. But it all has to be sturdy because it's going to be permanently mounted on top of my roof. So everything has to be hurricane code to 150 miles an hour. But while I'm writing the software and testing it out, I didn't want to have to keep climbing up on my roof to maybe unplug the camera or reset it or position it differently. So I made this adapter. This is the kind of metal tube. It's very heavy aluminum. It's called EMT. That'll actually be used to mount it up on the roof. And you can see it's securely mounted here. There's very large, heavy threaded couplings that will be sealed with thread sealant and we'll have Teflon seals and then thread sealant to seal it all off. This flange will actually be used to go in the wall, and there'll be a J-shaped pipe so that the camera points up and then it goes into the sidewall of the house. But in the meantime, I created this plywood mount for it to just sit on top of there, so I can just drop it outside on my flower box on the front of my house. And if you've seen in previous sessions where I've used the camera to try and take pictures of things, that's what it was. It was the camera on this post on the plywood, just sitting on my flower box outside the front of my house. So mounting it outside permanently. There's a lot of gobbledygook here, but this is how it looks. So I added foliage here. So not only does it have to be above the roof, the top of my roof, it has to be above the top of my roof. It also has to be out of the way of any trees or things like that that might block the view. And the way I'm going to have it set up on my roof, I will have an obstruction to the north, but then I don't have to look for Polaris because it's fixed and I'll line it up once. I can see to the south and I can see to the west. I will have an obstruction at about 30 degrees elevation to the east. That's just trees along the highway behind my house. But aside from that, I'll be able to see a good view of the west. And for South Florida, a lot of things happen in the west at night in the west. Here's that EMT conduit. You can see that there's a bend and there's couplings along the way. And then it goes in through that flange that you saw into a hole into my house, goes to a lightning surge suppressor so I don't fry anything inside my house. It goes to the power over Ethernet to supply power to the camera, which also has a GFI in case things want to pop. And then it goes to the router inside my house, and then I can connect anything in my house up to this. And I've got specs for the camera and where you can go buy one. I've got specs for the piping and for the wall mount. These two brackets right here. You have to get them a certain distance away from the eave of your house. And I happen to have 16-inch eaves. So I've got a fairly deep shadow here. I want to get above and outside of that. So I need an 18-inch standoff wall mount. And you can buy these things for antennas for your house. And so I'm just using it for this. Okay, and that collar you saw at the bottom, it has the 4 screws in it. That's actually a piece of aluminum pipe that was a nipple. It had threads on both ends and a flat area in the middle. I hacksawed off the threads on one end, so it had a nice open end. And then I drilled 4 holes in it. And then I took brass pop rivets that were threaded on the inside, and I turned them backwards and I tapped them into the holes. So now the screws go in and they fit into this collar that's on the bottom of the camera. So now I have my 150 mile per hour. It's not going to rip the camera out of this metal pipe durability. If I went with the original mount, it only has 3 screws and they were aluminum, not stainless steel. So that would be borderline. It might do 120 mile an hour, but it wouldn't survive 150. Since the Raspberry Pi computer, as well as my Windows laptop that gets the images, has HDMI output, I can put this up on my big screen TV inside my house. And I can actually put it up on Wi-Fi inside my house as video. And the benefit of that is if I can make it produce video out, I can connect it to Zoom through OBS Studio. So once I get it up and working, I'll use Planetarium software to point it and line it up and get the image in. And then I can show you the current look from the camera on the Zoom sessions in 4K. And I just mentioned that. I use VirtuaCam to make it work with OBS Studio. And if I wanted to say, well, how is that all going to work so that people on the Zoom sessions can see it? This is the end-to-end of that. You can see the pan-tilt zoom camera. You can see the INDI servers and drivers. And then that's talking to the Planetarium application, the imaging application, and it produces video. And then I can use VirtuaCam to connect that into OBS Studio, which I then do my Zoom connect into the internet. And now all the attendees can see what I'm seeing through Stellarium and the imaging application to what the camera sees. Now, leaving it outdoors, the camera itself is what is known as an IP66 grade weatherproof camera. So it's more than capable of staying outside in the rain, but that's with it pointed down. By pointing it up, I now have to put the glass dome over the top of it. Otherwise, the water would go into the motor area. And we don't want that because we corrode it. Once I put it out there, if code enforcement happens to see it and go, are you spying on your neighbors? I can explain to them, it can't get down below the horizon and it's above the height of my roof. So it can't look down into neighbors' houses. And it's for astronomical purposes. And it can look all the way upward. So long as he doesn't ask me, you know, we got an airport nearby. Are you spying on airplanes? No, I don't plan on writing the software yet to make it track airplanes, but I could. So what kind of observing targets would we look at? Well, obviously, this is not a $1,000 telescope and tripod mount, and it's not a $700 astro imaging camera. It has 18x optical zoom and 30x digital zoom. So you're not going to be shooting the pillars of creation, the Eagle Nebula, or the faint threads of the Veil Nebula. Besides that, from your house, you're going to have so much light pollution, you couldn't see those things anyway. The exposures are limited to 1/25th of a second. So you're not going to have like a 3-minute exposure. But then from city lights, you wouldn't get a 3-minute exposure anyway before the lights would bloom things out. Of course, you could shoot in different wavelengths. You could shoot in hydrogen alpha, but then you got to spend the hours coloring it all in. So the targets you'll pick are things like the moon, obviously, it's a 1/2 degree. Bright planets, we've got some amount of zoomage for that. Any larger, brighter deep sky targets like the Orion Nebula. Meteor showers. If you just point it at zenith overhead and you let it shoot video for 2 a.m. to 4 a.m., it's probably going to capture some meteor showers if there's a meteor shower prominent that night. If I get to the point where at wide field, I can point it at the same spot in the sky day after day, I can then do a snapshot of the sun as it traverses that sort of stretched out figure 8, the analemma. But it will need protection if you're going to do things like, I want to see sunspots. Yeah, you'll try that once and you're going to say, I want to buy a new camera. This one's burned up. Okay, the downsides, obviously no multiple second
That is
exposure.
one more thing that you could add to your observation.
Yes.
You could, if you can write a program to actually track satellites, it will be nice for you to look at the Hubble Space Telescope or the space station.
You're not going to have enough magnification. If you look at some of the stuff that Arno's done, it's more than 400x magnification to be able to see, like, as the ISS goes across the face of the sun, where you can see the solar panels and such.
No, I don't mean across the sun. So I've looked the space station with my pair of binoculars. That's might be similar to the magnification you would have on your camera.
Okay.
You would be able to see the solar panels, and it's not like really detailed, not go like terribly good on you, but you know, it could be something fun to actually follow, because this is stuff that gets people excited. To see the
Yes.
space station is always like a nice thing to point out, or
Well,
any other satellite.
Well, also remember, Stellarium can track satellites, so I could actually have it do a go-to and track of the satellite.
It doesn't even need to have very detailed imaging. It's better. It's most likely better than me following with my pair of binoculars and trying to see something.
Yeah.
So it's
But also at wide field, you can point it to where a satellite's going to start to appear and then where it's going to disappear.
Yeah.
So you can actually take a video of it coming out of nowhere, appearing, getting brighter, 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 dimmer, 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 and then disappearing.
That's a cool thing. So
I
add
made a note. I made a-
satellite tracking.
I will. I've added a note. So when I get the drivers farther along and I'm starting to test it out, I'll try for satellite. And if SpaceX launches another constellation of satellites, 500 satellites, maybe I can catch them while they're still all grouped together, and I can threaten astronomers with it. Look, they're going to destroy everything in your life. And then 3 months from now, you can't even find them. So current stumbling blocks, all the stuff in black, I've already done with those. The stuff that's in red is the stuff I'm currently working on. So in order to make sure that I had my OnVIF commands correct, I actually wrote some Python script that would say, okay, I want to test out this feature. So I would code up the Python script to do just that and only that. But I would cut and paste it from multiple thousand lines of Python, and then I would just uncomment out the part that I wanted to do so I could prove that, yes, that's the command sequence for doing that function, like turning off the infrared LEDs. So I would have a camera. I'm actually in my house right now. I've got a camera that points at the other camera, that points out the astronomy camera. So when I do things like turn the LEDs off and on, I can actually have the camera that's pointing at it see, yep, the LEDs are on, yep, the LEDs are off. Or if I turn the camera to a certain direction, I have another camera that's looking at it saying, look, it's moving. Okay, it's now in the right direction. So I've got my own test environment to be able to test these things out. So I'm now in the process of taking those Python sequences and recoding them as C++ as parts of the INDI drivers. So that's where I'm at now. But if you want to know, well, soup to nuts, once all this is working, this is the set of steps that you would do. Basically, turn on the camera, note where it is on your home network, note the IP address of it, start up the Raspberry Pi computer, which will start up the INDI server and the drivers, and note the IP address of the Raspberry Pi. On your Windows or your Apple or whatever, run up your planetarium software, Stellarium or K-Stars or Cart to Seal, or run up your planetarium software and configure it to use INDI to talk to the Raspberry Pi at its IP address, configure the INDI drivers for the IP address of the camera, and now you can command your planetarium software to say, hey, slew the planetarium software to the moon. And you can now see the simulated image of the moon in your planetarium software. And now you can say, and hey, planetarium software, slew the telescope to the moon, to where I'm currently pointing. And that will go to the INDI server, to the INDI drivers, to send out the OnVIF commands to make the camera point at the moon. And then you'll sort of use your move commands to get it dead center in your field of view. And then you can start your astronomy image capture software, CCD Seal, which is also made by the guy that does Cart to Seal, or ECOS, or even PixInsight. For those people that have spent their couple of $100 on a copy of PixInsight, there's a thing called INDI Client. It works with PixInsight, so that PixInsight can command your telescope mount and your camera using the PixInsight user interface. So you configure it up to talk to INDI, to talk to the Raspberry Pi, to talk to the camera. And now you can command it to zoom and focus to get a good preview image. And then you can do a snapshot, or you can capture a streaming video file. And then when you're done, you tell it, hey, park the telescope, and it will move the camera around to hopefully north and zenith, north and horizon level, so that it will point away from where the sun might be, just to keep the sun angle off the camera. And then you're done. So that would be a session. Now, if you have the camera already on the network, already on your home network, and you have the Raspberry Pi already up and running on your home network, you already know what the address is. And if you're running your computer, firing up Stellarium is pretty straightforward. If Stellarium has already been configured to use INDI and to point to the Raspberry Pi and the camera, that's already pre-configured. So in a matter of a couple of minutes, you're going to have the planetarium software being able to slew at some target in the sky, and then have the camera point there, and then you can zoom up on it and focus it, and you're going to be looking at the object. So if you sort of walk outside your front door and you look to the west and you go, hey, there's something bright out there. You can fire up Stellarium and it will say, oh, look, that's Venus. And then you can tell the telescope camera, go point to Venus, zoom in on it, focus it, and now you can see what phase Venus is at. So you can do stuff like that. So the almost instant gratification of the ad hoc use of it achieves the expectations. And as I've often said, we won't have pudding yet until I can show you some images from it. So no pudding images yet. The camera's on my home network. The Raspberry Pi is on my home network. I've set up a file sharing interface between my Windows development laptop and the Pi. I'm writing the drivers in C++ using Microsoft Visual Studio, and I'm setting up the compiler that generates the code so it will produce ARM processor, which is what the Raspberry Pi uses, in a Linux operating environment for the Raspberry Pi. Once I have the three drivers basically fleshed out, written, and they're compiling, then I will transfer them over to the Raspberry Pi, where I'll do the final development and testing on the Pi itself using a development environment over there. Once I have it over there and it seems to be working, I need a second opinion. There are many amateur astronomers that understand INDI, and I will submit to a GitHub site the drivers. And the moment that you have people that understand ONVIF surveillance cameras and also do amateur astronomy and understand INDI, and they see that there is an INDI to ONVIF set of drivers, it will definitely attract their attention. And if it works well enough, then maybe I can convince the INDI development team to add this as a third-party driver to the next release of the INDI software. And now you have many thousands of INDI users that can go out and buy a relatively inexpensive hand-tilt zoom camera and use it for ad hoc observing. So that's ultimately like the audience I want to get to. So in conclusion, if you're one of those amateur astronomy types that are trying to take pretty pictures for the astronomy picture of the day, the APOD, or you want it for magazine articles or for catalog pictures, then this is probably not the kind of camera you'd want to use. You'd want to spend a lot more money and a lot more time. And if you're into high-end deep sky astrophotography, where you spend many thousands of dollars, you have almost an unlimited wallet, and you want to go spend time in the dark of the Everglades, in the heat and mosquitoes, to get your pictures that then you then come home and spend 5 hours processing stacks of images and false coloring them and touching them up. This is not likely to be satisfactory to you, but to each their own. But if you're one of those people that say, I've looked at those fully automated telescopes and those suckers are $700 to $1,200, and they're a collection of these common denominators. You know, it's the cheapest camera on the cheapest telescope on the cheapest mount, but I can control it from my iPhone or my Android, which is very nice, but that's a lot of money for what shouldn't cost that much money. So for those people that want a permanent observatory at their house and they don't want to spend a lot of money, that's kind of what I'm looking for. And I've updated the list of web links for various pieces of information. So that'll be included in the video. And comments or questions?
Well,
I know
would
a lot.
comment
I've heard a lot of it before.
that would be super cool if you got to get like one, when you get all the kinks done and stuff, you would, I bet you totally would impress those doctors astronomers, the one that we did before, like when we visit one of the conferences. That
is the American Astronomical Society. You have professional astronomers whose eyeballs have never touched the eyepiece of a telescope, which is an amazing concept. You have planetary scientists. These are people with advanced physics degrees and planetary astronomy, and they've never actually looked through a telescope. They sit in their office somewhere in Chicago and they have a telescope in South America, take a picture and email it as an attachment to them. They may never have been at the telescope. In fact, if they visited these observatories that cost hundreds of millions, if not billions of dollars, the technicians that operate and maintain the telescopes would not let those hack astronomers
Lock the
anywhere
doors.
near their precious toys. Yeah. If it all works well and the INDI community seems satisfied with it, I would definitely promote it outwards to the amateur astronomy community. Maybe consider an article in Sky and Telescope or Astronomy magazine. Maybe do a special Broward Astronomy YouTube session on just showing it
How
in
to.
operation. You know, don't tell people all the gobbledygook I just told you. Just go, hey, looky what I can do. And this is what I made. And then have somebody go,
Clickbait.
how'd you do that? Here's 3 hours worth of video you can go watch. Yeah, this has very deep legs and hopefully a very long future.
So this is good for outreach, because sometimes like people don't have time to wait for pictures to stack for you
Mhm.
to actually see something, and then you call her, and then that's the
Yeah.
little detail. This is like instant gratification kind of thing, and that gets people talking. Like the beginning of explanation, what is a planet, the phases of Venus. So it's the simple astronomy what you start, you know, you don't have, like the first time you look at Saturn, all you see is just a blob with the ring, and that
Yep.
gets you stuck in astronomy forever. So it's pretty cool to have something that looks simple,
Yeah.
to actually show you know, the public that that's a really good idea to get something like that working.
Yeah, think of it this way. If you have serious amateur observatories that are willing to spend $1,000+ on a camera for the back of the telescope, but let's say they have inclement weather like we do in Florida, and they have to worry about, you know, dome or roof opening and closing, and now you can have, for probably $700 or less, depending upon what you've got lying around, you can have a telescope that is weatherproof, that, you know, the clouds part, and you can, within a matter of minutes, be observing for public outreach at the observatory. Or if you have to drive to the observatory, you can fire this thing up over the internet and look up and go, oh, well, it's clear at my house, but it's overcast at the observatory, so I'm not going in. So there's a lot of potential uses for this beyond just amateurs setting it up at their house. So like I said, I think it's got long legs.
And the other thing is that the same things that you are doing, I bet the solution would be way much simpler just for meteorology. So that is another, not just the astronomy, but meteorology, because you can actually see the sky, and you can, it's that would be a good solution for that too.
All I can say is, if you had one of these on a 4G accessible connection at Sea Grape Drive, Harold Campbell, yes. So if you had one of these at Sea Grape Drive and another one at Harold Campbell, you could literally, before you ever left your house, look up and see what the sky looks like. You would have at least a 30-minute head start on it, because a lot of times people will drive to these sites only to find out once they got there, it was completely overcast, but at their house, it was perfectly clear. Anyway, that's the idea, is instant gratification, ad hoc setup and tear down that doesn't require much. If you're thinking of permanently installing an observatory at your house, this is much cheaper than the actual observatory dome would cost you, let alone the installation for it and the electrical for it. And you don't even have to have additional wiring installed at your house. You know, you don't have to, it's not like electrical charging for your new electric car. You don't have to go get an electrician to come in and wire up a 60 amp circuit breaker for you. This is
Well, it looks like you're concerned about lightning.
That's not so much something I'm concerned about. It's something that if code enforcement does rear their ugly head when I go put this thing out there, it will look like somebody who's paying attention did it. So I'm using aluminum EMT conduit, heavy gauge, much larger diameter and thicker than I really need, and using stainless steel hardware and galvanized brackets. So like it's going to be sturdy and it's going to last a long time. And you can see I paid attention to lightning suppression. And if they do want to come inside and see how it's wired up, I have a ground fault arrestor on the inside. And, you know, it's only 48 volts. It's not 110 volts to the camera. So I'm paying attention to a lot of things that I don't really need to. It's in case it gets scrutinized by certain others.
Also, I'm interested. I'm curious about your focus adjustment.
Yeah.
Seems to me it's all infinity out there. Do you need a focus adjustment?
You need a focus adjustment. I've always been perplexed by the optical physics of this. If you took a camera, let's say DSLR with a 50 millimeter lens, and you focus at a target that's 20 feet away from you, you have to focus to a certain adjustment. If you then focus to something that's several hundred feet away and you get it in focus, you have to, you know, adjust the focus.
Yeah.
Makes sense. And you probably have done the, if I focus it this way, I can see the chain link fence that's between me and my target. If I focus it at infinity, the chain link fence magically disappears and all I can see is my distant target. That's actually a thing in cameras and optics. Okay, I understand that there's this whole concept of rays of light needing to be parallel, and that's why you need to so dramatically change the focus is to converge the beam path of the lens to a focus spot at a certain distance where it hits the sensor, and I get all that. Now, let's do astronomical imaging. If I want to point my telescope at the moon, I have to really crank the focus. I have to get it way back there. And now I've got the moon in focus. And then I want to take a picture of Jupiter. I have to move the focus back in quite a bit. Not as much as I had to move it out, but a good portion of it. Okay. How much distance do I have to go through before the rays of light are essentially parallel? Because if I want to change my focus from Jupiter to Saturn, I have to touch up the focus a little bit, which may only be a millimeter difference in my focus distance. But a millimeter difference for rays of light that have to travel 400 million miles. I think there's something else going on there, folks, but we'll accept this light convergence thing. Now, I want to focus beyond Saturn on the Orion Nebula. I have to tweak the focus a little bit. And the Orion Nebula is what, over 1,000 light years away? So the difference between Saturn at less than 1 billion miles and something that's 1,000 light years away, and a light year is 6 trillion miles. That's 1,000 times 6 trillion miles. And I have to tweak the focus a little because the light rays aren't parallel yet. I don't get that. But the one that really is baffling is I'm focused on the Orion Nebula, which is 1,500 light years away. I now want to focus on something that is 3 million light years away. Just a little bit. Just a little bit. Not even a millimeter distance change in the focus. So yes, I will have to be able to adjust the focus. Infinity always winds up being the extreme one end, and the closest approach of focus is the other end. And everything in the middle, be it, you know, dozens of feet to, you know, 1,000 light years, just a little bit of focus, but it gets to be less. I postulated at one time that photons have a property that we have yet to realize, which is there's a property of photons that is related to the duration of existence of a photon. So if a photon is coming from a distant galaxy many light years away, that photon is on a continuous path. It doesn't hit something and get regenerated. It continues to exist for that, very long, many years duration. And this property changes. And so that is why you're having to adjust focus. And that scales correctly. If you look at the scale of that and you plot points along the curve, you can actually see that there's actually a curve that you could mathematically associate with the property of a photon as it travels over distance. And that property is very much weaker for photons that have been in existence for a very long period of time, which means your focus can be at infinity. You don't have to do much convergence on the light. And that gets into that whole parallel rays of light. They're more parallel. I don't think it has to do with parallel rays of light. I think it has to do with the property of photons we have yet to realize. Now, if the photon is relatively new, it was just emitted, a few nanoseconds ago from the object that you're taking a photograph of, that property is still very strong. So you need to do a lot of convergence of the photons in order to get the image in sharp focus. That's the other extreme of it. So I think, someday we'll figure out what this property is, but I think it's a property related to the duration of existence of the photons. But, even Isaac Newton towards the end of his life said, I just don't get photons. He still had a lot of not quite understanding the behaviors of photons. And until Einstein came along and said, I've got this theory called the photoelectric effect that relates photons to wavelengths of electromagnetism. There's that. But explain focus. Explain the differences between focus at a short distance and focus at longer distances, and then focus at thousands to millions of light years. Still got to tweak it just a little.
You must have to have a very fine adjustment in your camera then.
Oh, you do. It has to be able to change the focal distance by a fraction of a millimeter.
Can you do that with your little surveillance camera?
Yes. Any motorized focus, if the gearing is sufficient, then you're not looking to turn an actual complete rotation of the gear. You're looking for, one or two teeth turn of the gear. But because it's plastic mechanisms, you may have a backlash, so you may have to move it a little bit past it and then bring it back to it, which is why the imaging software has a focus adjustment in it where you can go, okay, what speed do I want to adjust the focuser? You have a rate of 1 through 10. And then how far do I want to adjust the focuser? Do I want to adjust the focuser by seconds or fractions of a second, or just touch it? And when I touch the button, it moves it at speed 1, which is the slowest speed, for just 1 pulse. So it may get down to, you have to do a plus and minus a couple of times to get the backlash out of the focusing mechanism to take it down where you can do a focus adjustment that's a fraction of a millimeter. But I am aware that, and Fred Lehman was a great guy for doing this. If you have to adjust the focus of your telescope for your imaging by turning a knob with your human hand, you're not going to get the focus perfect. What you want is to be able to have a very large geared motor, and you rotate it a very small fraction of a rotation, and you want to have a closed loop that will couple analysis of pixels in your image to the focus gearing mechanism. If you look at a pixel close up, you're not going to see a square that's a certain color. You're actually going to see the channels of color. So you're going to see red, green, and blue. And if you look at a pixel of an object and you know, well, I know that I'm shooting it in hydrogen alpha, therefore it's going to be a grayscale, and I want a certain balance of my red, green, blue. As you change the focus, you'll note that the levels of red, green, and blue vary. And when you get all three of those balanced out, it's dead on focus. It's perfect focus. You cannot get it any better until the South Florida humidity goes wobble, and then your focus changes. So that's why most people don't try and get to that level of focus. You want that level of focus if you're in the Atacama Desert in the midst of night and you have a flat temperature and flat skies. Then you want that high precision focusing. But focusing as cones of color on a single pixel on the edge of a deep sky object, that was just wonderful. So maybe I'll get to that someday, but not yet. But yes,
I wonder if stepping motors are fine enough to adjust small little differences.
I don't have any clear understanding of whether the pan, tilt, zoom, and focusing within the camera is steppers or what's the other one? Steppers and not synchronous.
Continuous.
Yeah, I could
Brushless.
yeah. But you want them to be brushless because then they'll last longer.
Induction, something like that.
Yeah. Servo. Stepper motors or servo motors. And depends upon whatever part they got cheapest at the time as to whether they're steppers or servos. And they all have their pluses and minuses. Steppers have something called jitter. So if you're holding it at a certain position, if it's between steps, it'll jitter.
Yeah.
But if it's
Or
a
hop to the
servo,
next step,
if it's a servo, you energize the coils and it goes around to a certain position. You turn off the energy of the coils and it just sits there. So they have their pluses and minuses. But the camera is what the camera is.
Yeah.
And if it turns out it's not the best camera for this purpose, I'll bet it's a great camera for looking at the moon and maybe some of the brighter planets and brighter deep sky objects. But we shall see.
Keep us posted what you do.
Yeah. Well, I'll show you what I've got sort of further down the road a bit. I don't know if you noticed it or not, but the camera aperture is the same size as a 2-inch telescope eyepiece. This is a 2-inch filter ring, and it has screw threads on the bottom and screw threads on the inside. And you can buy a second one of these and you can screw them together. If you want to put a filter inside, all I need to do is expose the threads on the end of the camera, and I can screw this onto the end of the camera inside the dome, and now I can have an always on, light gray filter. But think about it for a moment. I probably will never use the 1x zoom. I never really want to see like 180 degrees field of view. It'll always be 30 degrees or less. So I really do not need the camera to focus at full wide field. So what I did was I bought a lens, and this lens is a 2x. If you were buying a Barlow lens, this would be the prime lens in your 2x Barlow. Fairly thin, large clear aperture that I just put my finger on.
You're upside down.
Yes. Well, that's what a lens will do. It'll make it upside down. But the idea was this was claimed to be a 2-inch camera lens. The problem is it's 2 inches. It needs to be, instead of being 50 millimeters, it needs to be like 45 millimeters to fit inside the thing. You can actually see the edge of the lens sticking out over the edge. So I need to find a source of a 45 millimeter lens. And wouldn't you know it, I already found one. I already have one.
Edmund Scientific?
No. Those suckers are a ripoff. They want $400
Oh, yeah, sure.
for a lens like this, but it's technical spec. There are no Mars defects or anything. It's a perfect lens for scientific research, but I don't need it that good. I just need it like commodity grade. So when I go to astronomy events, there we go. When I go to astronomy events, this is one of the things I take with me. It's a little box, so it's kind of weatherproof. And inside the little box I have,
We can't see it.
I know I had to pick up the, I keep some of those gel packs inside here to keep the Florida humidity out. This is a 2-inch, genuine 2-inch Barlow lens that I put in my telescope to magnify things. But this is a very nice Barlow lens because it's modular. And what I typically do is I don't need a 2X because my Maksutov Cassegrain telescopes produce a lot of magnification automatically. But what I can do is pull the lens cap off the bottom. And you see the black part here?
Yeah.
There we go. I can unscrew that. And it gives me a 1.5X Barlow. Like that. And that actually screws in to the mounting. Exactly the correct threads for it. So now the only problem is I need enough clearance inside the glass dome to accommodate this. But I can actually buy a cheaper version of this same modular Barlow, and I can rob the lens out of it. So that instead of having a 50mm lens, I have a 45mm lens. So if I find one of these Barlows on sale, I can disassemble the back end of the Barlow, and I've got my lens. Because I don't know if you can see that on the camera. I don't think it's going to focus. I don't think it's going to focus on that.
Oh, yeah, we see it.
But inside here, there's a ring that I can unscrew and take the lens out. So what I'll do is I'll find one of these on sale. It doesn't have to be any particular brand. This is a GSO out of Japan. And it's very good. And I get it through Agena Astronomy, Apogea. And if they have one of those on sale, I'll pick up one of those and I'll use it for parts, as the saying goes. And then I'll have the ability to do at least a 1.5X on whatever the zoom is. So if the zoom is 8X optical, I'll get a 12X optical zoom. And that's how I'll make things bigger. So I thank you for the feedback and for listening.